second part of your video for 5.3, connecting f prime and f double prime with the graph of f. And we're going to pick up here with example 5. There are parts of this that I'm not going to write down. They are in your textbook, and I think they're covered in the book video as well. So just know that some of this I might be skipping through a little bit. So we have example 5. We have a particle moving along a horizontal line with the position function x of t. Notice they're using x instead of s. That will happen once in a while. Is equal to 2t cubed minus 14t squared minus 22t minus 5 for t is greater than or equal to 0, so I'm not considering any times before 0. We want to find the velocity and acceleration and describe the motion. So my velocity is going to be the first derivative. So that's 6t squared minus 28t minus 22. To describe the motion, I need to figure out where the velocity is equal to 0 and then check and see what kind of sign changes I have, and then I can talk about how it's moving. We can divide all of these by 2 to make the problem a little bit smaller and easier to factor. So this is going to be 3t squared minus 14t minus 11. This does factor. 3t and t, I'm trying to make 14, so I want the 11 here. I think I messed a sign. Yes, I did. 22, this is positive. Okay. So those are both negative, and that's going to be 1. Negative 11 minus 3 is negative 14. So we get 11 thirds and 1 as our two values here. And so if we look at a number line, and I'm actually going to scroll and give myself some more space here for this. We won't need as much for the acceleration because we're going to be going down quite a bit as far as the factoring goes. I am starting at 0, so I don't need to consider anything before 0. So there's my 1. Here's my 11 thirds, not pi over 3. Tell I'm doing calculus where my mind is. Try to write 11 and then write a pi. Okay, so 11 thirds. So if I think about things that are in between here, and I'm going to be looking at the sign of x prime. So I can consider 1/2, I can consider 2, and then I can consider 5. So x prime, that would be the same thing as v. If I plug in 1/2, let's say I plug it into where I have this factored. Well, 3 times 1/2 minus 11 is negative. 1/2 minus 1 is negative. When you multiply those two negatives together, you're going to get a positive, which means your particle is moving to the right. It has a positive velocity, so it's going to be moving to the right because we are looking at the horizontal. If I plug in 2, 3 times 2 minus 11 is negative. 2 minus 1 is positive, so that's going to give me a negative. So from 1 to 11 thirds, excuse me, we're going to be moving to the left. Now if I consider the 5, this is what happens when you make a whole bunch of videos in one day and you're not used to talking. When I plug in the 5, 3 times 5 is 15, minus 11 is 4, so that's a positive. 5 minus 1 is also a positive. When you multiply two positives, you still get a positive. So that's going to be moving to the right. So whenever we talk about the velocity here, your particle is moving to the right from 0 to 1, and from 11 thirds to infinity, and that's the reason being that's where the first derivative is positive. It's moving to the left from 1 to 11 thirds. So that would be enough to describe our motion there. Now if we look at the acceleration is going to be the derivative of the velocity. And again, I should go back to the original function there. So that is going to give us, or rather the original velocity function before I divide it by 2. That's going to give us 12t minus 28. So I'm going to set that equal to 0. So I have 12t is equal to 28. T is equal to 28 over 12. Both of those can be divided by 4. So that's going to give me 7 thirds. So 7/3. If I'm looking at the A, which is the x double prime, I can pick 1 and 4 as my values that I plug in. If I plug in 1, 12 times 1 minus 28 is negative. If I plug in 4, 12 times 4 minus 28 is going to be positive, which means this is going to be concave down and concave up. It is decelerating here and accelerating here because it has a positive acceleration. By the way, if you want to, this is not saying decelerating and acceleration is not slowing down or speeding up. To figure out whether something is slowing down or speeding up, you need to compare velocities to acceleration. If the velocity and the acceleration have the same sign, then your particle is speeding up. Whether it's speeding up in the positive or negative direction doesn't matter. If your velocity and acceleration have different signs, one positive, one negative, then it's going to be slowing down. So for this particle, or for this explanation here, the accelerating force is directed left from 0 to 7/3, and then it's momentarily 0 at 7/3, and then it's directed right from 7/3 on. And again, your book does go through a good explanation of that, so if you didn't quite understand what I was talking about for my explanation, please go through and read your book for that one. On page 217 is theorem 5. This is an alternate test for extrema. The alternate test talks about using the sign of the first or the sign of the second derivative as well as where the first derivative exists to figure out if you have a maximum or a minimum. So I do encourage you to read over that. We're not going to be using that a whole lot, but it is helpful to have another way to find the extreme values. So for example 6, if we want to find the extreme values here, the first thing we need to do is the derivative. So that's 3x squared minus 12. We do need to set that equal to 0 to figure out where this works. So we get x equals plus or minus 2. So now, to find those extreme values, we need to find the second derivative, or to figure out what they are there. So my second derivative is going to be 6x. Now, to figure out what you have here, we want to take those values that we had for the first derivative and plug them into the second derivative. So if I plug -2 into the second derivative, I'm going to get -12. Well, since I get a negative number, that means it's concave down. And if you have something that is concave down, that's going to have to be a maximum. So that's the relation there. If the second derivative is negative for whatever value you get when you find the first derivative equal to 0, then that is going to be a local maximum. If I plug in +2, I'm going to get +12. So that's positive. That means my graph was concave up here. And if you have something that's concave up, that is going to be a minimum. So we have local max at x equals -2 and a local min at x equals +2. And if you want to actually find what the whole point was for the local max or local min, you would plug those values back into the original function. Okay, now we have one that has a couple of different parts to it. This is example 7. We are given a first derivative to start off with, and then we're going to go through and find some different pieces of information with this. So part A, identify where the extrema of f occur. We are already given the first derivative. We don't have to take the derivative yet. because I know the first derivative, but I do have to set this equal to 0 and solve. So if I do that, I can factor out a 4x squared, and I'm left with x minus 3. So I get 0 and 3 is my values. I do have to test those on a number line, because if there is no change in sign in f prime in the different regions, then there are no extreme values that are happening here. So I'm going to have to test -1, 1, and say 4. So -1, and I'm going to plug into my factored format here. Because I have this 4x squared on the outside, that's always positive, so I'm really just concerned with what the sign is on the inside. So f of -1 is going to be negative, so I'm decreasing there. 1 would also be negative, still decreasing, and then 4 will give me a positive. I can't actually find the value of the local. This is going to be, since it's decreasing and then increasing, this is going to be a local min at x equals 3. But I don't know for sure what the y value is there because I don't know the original function. All I know is that the local min has to occur there because that's where the derivative changes from negative to positive. 0 has no effect on the extrema because there's no sign change at 0. We're decreasing before 0, we're decreasing after 0, so there may be something else going on at 0, but it's not an extreme value. Okay, now we have part B. Find the intervals on which f is increasing and where it is decreasing. Well, I already have my work set up there for this increasing and decreasing. So I know that I am decreasing from -infinity to 3, and I'm increasing from 3 to infinity. Because I already did the work. I already figured out where the first derivative was negative, where it was positive. Okay, part C. Find where the graph is concave up and where it's concave down. For this, I'm going to have to take the second derivative. So if you recall, the first derivative was 4x cubed minus 12x squared. So my second derivative, I'm going to switch colors for this. My second derivative is equal to 12x squared minus 24x. So if I set that equal to 0, I can factor out a 12. I get 0, and I get 2 as my values. So if I test those on the number line, again, I need to pick something in each region. So like -1, 1, and 3. I'm going to plug them into the factored form because it's going to be easier to tell signs. So if I have -1, that's going to be a negative value and a negative value. So when I multiply those, I'm going to get a positive. So I'm going to find the sign of f double prime. If I plug in 1, I get a positive and a negative. And if I plug in 3, I get a positive and a positive. So we're concave up, concave down, concave up. So concave up from -infinity to 0, and from 2 to infinity. Concave down from 0 to 2. And then we need to sketch a possible graph for f. So I'm going to put together everything that I found with the first derivative and with the second derivative. Just going to put it all together into one big thing where we can figure out where everything is going on. Okay, so the values that we had. I got 0 as an answer. I got 2 as an answer. And I got 3 as an answer. So I'm going to state everything that I know about the function between these different intervals, and then I'm going to sketch something that fits that. So if I look back at my work for part B, or actually for part A, whenever we were looking at that, less than 0, my graph was decreasing. From actually 0 to 3, it was also decreasing. So that means 0 to 2 was decreasing, and 2 to 3 was decreasing, and then after 3, it was increasing. So whenever I draw my graph, it's going to be decreasing down to 3, and then it's going to start increasing. Now if I look at my concavity, less than 0 was concave up. 0 to 2 was concave down. 2 to 3 was concave up. And 3 on was also concave up. So I have all of this information here, and I'm going to then go through and sketch out my graph and get something that matches with my situation. So I have my 0. I'm going to go ahead and mark my 2 and my 3. It doesn't really matter where you start this on the y's, because we don't know what that original constant was of the original function, because I was only given the derivative to start with. I do know I have to start off decreasing and concave up, but I'm going to switch to concave down at 0. So I'm concave up until I get to 0. Then I'm concave down, but I'm still decreasing till I get to 2, where then I turn to be concave up again. And I'm going to make this a little bit more extreme with my switch here. So we're going to come in, concave down, concave up, and then I'm still concave up. So you should have this point of inflection here. And I also have a point of inflection here. So there's up, down. I know this should be a little smoother than what it is there. I hit red, apparently I did not. So this should be a little bit smoother there. And then, so there's your 2 points of inflection, and then down here at 3 is where it switches from decreasing to increasing. So that would be a possible graph for everything that was going on here. This is the last example we're going to look at, and I'll scroll up here in a moment so that you can see the graph of what we have here. So the original function is continuous on this interval -4 to 4. The discontinuous function f prime has this domain, so you can see 0 is not included, 2 is not included in the domain. We want to find the x-coordinates of all local extreme values and points of inflection. And then we also need to sketch the graph. Well, I already have the graph sketched out, so I'll go down to that here in a moment. So we have some different things that are going on here. We know we're looking for local maxes, local mins, and then we are looking for inflection points. I don't think I have those on my original paper, so that's something we'll have to go through and add. So local maxes. Local maxes occur when you are increasing and then go to decreasing. So that's where you go from positive to negative with f prime. So we have a local max at -3. We have a local max at 0 because it said the original function was continuous, and I'm positive leading up to 0, and then after 0 I'm negative. And then we also have another one going on at 2, because even though the function is not continuous there, or the derivative isn't continuous, the original function is, and we are jumping from positive to negative. Now, endpoints. Consider your endpoint. If you have an endpoint, like for example, this left endpoint here at -4, at that left endpoint, we start out we have a positive slope. So if I have my endpoint and I'm going up, that endpoint is actually going to be a local min. For my right endpoint, if I'm going down, leading to that, because this was a negative slope, so it would be decreasing down to that, this is also going to be a minimum value. So I'm going to add that on after I look at the other minimums. Minimums are places where you go from negative slopes to positive slopes, or where with the left and the right endpoints you need to think about if you're increasing or decreasing leading up to it. So at -1, that is also going to be one of our values. +1 is another, and then as we already said, 4 is going to be another place where that happens. Inflection points are going to be where you change concavity. You're going to change concavity at places where your derivative would have a slope of 0. So this derivative is going to have a slope of 0 at -2. And actually, concave down, concave up, that's the only one. -2 is the only inflection point because this is the only place on this graph where we would have a slope that's equal to 0. Because if I sketch the derivative of the derivative, that would be crossing the x-axis at -2. This is going to be a straight line. This is going to look kind of cubic. Well, this is a linear function. This one is also, this one's actually going to be quadratic. So just when you think backwards of these different things, keep that in mind. And here is our possible graph. Notice the only point of inflection that I have is right here. Because I switch, I'm concave down, and then I'm concave up, and then I'm concave up, and then there is no concavity with linear functions. So this is one possible graph that you could have the original function at. That's going to wrap up our examples. I know this section has a lot in it. You may have to go back and watch these videos a couple of different times before they really start to sink in and make sense. But go back through, re-watch this if you need to. Your homework is due on Monday. Go back and watch the first part video as well, and reach out to me if you have any questions.